Yeah, I'll just get it. Thank you. So, can we reimagine this next generation network from the requirement of communication, sensing, and security? So let's look at these requirements, right? So one of the common requirements for this device is their increased reliance on edge and cloud infrastructure for compute and inference. For instance, these autonomous vehicles generate tons of data from their sensors like LiDARs and cameras, which need to be shared among other vehicles or the infrastructure so that you can ensure safe and collaborative driving. AR/VR devices need high quality video streaming for immersive experience. Even IoT devices, there are millions of them, they require extremely low power connectivity. They don't have local compute, so they need to offload the compute and data to the server. While recently we have seen a lot advances in data centers, one of the main bottleneck that remains today is the communication link. We need to make sure that this communication link is extremely high speed. It is scalable to meet the demand of these diverse set of applications. It should be reliable. Otherwise, your car may go into accident or the video might freeze. And also, for many applications, we need to support mobility, device mobility. So if you look at the spectrum and the technology today, 4G and other technology works in sub-6 band, below 6 gigahertz, which is already overcrowded with just 400 megahertz of available bandwidth. Now, to support the new next generation of devices, we need to go higher in frequency. We have millimeter wave band, which has more than 2 gigahertz of bandwidth, enough to support these diverse set of applications and their high throughput demand. But with this high throughput, high bandwidth, we can imagine millimeter wave to be deployed in a dense area like a stadium or an intersection or a university where we have high density and meet all these device requirements. But today, millimeter wave deployment is limited to few tens of devices. So the fundamental problem is not the availability of resources, but it is the inefficient distribution of these resources that limits scalability. So let's understand the fundamental challenge. Fundamentally, high frequency waves attenuates faster in the environment. It is physics. While sub-6 communication can support multiple youth devices with an omni coverage, millimeter wave requires hundreds of antennas to create extremely narrow pencil beam to support these devices with similar coverage. Now, these narrow beams, as you can see, illuminate only a small region in space at a time. That means only a small subset of users can be served in one time slot. If you want to scale it to multiple devices, you need to either scan the beam or you suffer more delay and limit the scalability. At the same time, if let's say you wave your hand or a blocker or a vehicle passes your link, you can easily block it. The link will go down. It is not reliable. And when the device is mobile, you need to make sure that these directional links are aligned with every location of the device over time. So despite having high bandwidth, it is the existence of these narrow beams that limits scalability, reliability, and mobility in millimeter wave links. So my thesis develops novel algorithms and architectures which provides scalable and reliable communication for these links. At the same time, when I build the system and I look into the scalability challenge, I realize when there are multiple devices, it's very hard to track each devices with their complex mobility patterns. So I deployed high resolution sensing algorithms, which can track user movement with good accuracy and integrate it with communication infrastructure to provide sensing driven communication. And when we deploy this system, we need to make sure they are secure. So I developed and validated some of the attacks like the spoofing and jamming attacks, and I developed countermeasures to protect this infrastructure. My research has been across these three domains. I have published in these areas. In this talk, I will mainly talk about the work flexible in communications, a bit on reliable, and very briefly touch upon the topics on sensing and security with my work on Comrade and Spoof. The work Comrade was sponsored by Qualcomm Innovation Fellowship, and I have also spent 6 months at VMware to work towards commercialization of some of the techniques and research which are inspired in the market. So before going into more detail of my research, I want to give you a flavor of my research philosophy. When I look into a problem, first I understand the fundamental theory, how things work, what are the challenges, and develop some provable algorithms for solving those challenges. And then I build large-scale emulation or simulation platform to validate that theory and develop some good intuition of the problem. Finally, I enjoy building hardware and testbed. And through this building large-scale testbed, I try to make sure that the techniques that we develop are applicable in a real-world environment. And sometimes the hardware doesn't work, as we all know. It might be some hardware constraint that we might have missed in theory, or it could be that we kind of like didn't utilize some of the challenges that the hardware are capable of or they're not capable of. So we need to go back and we need to revise our theory and redevelop those algorithms so that they actually work in real world environment. So through this meticulous approach, my research kind of bridges the gap between theory and practical deployments. I have built multiple such research prototypes. Here you can see one of the millimeter wave testbed that we have deployed using phased arrays at 28 gigahertz frequency. We have built a new antenna array prototype that using some true time delay elements, which can scale millimeter wave connectivity to multiple devices. Here is a platform for radar and radio synchronized sensing. And then we have a millimeter wave reflect array, which can carry out a spoofing attack on millimeter wave sensing system. As you can see, all these test beds span across the three areas of my research. In the first part of my talk, I will go through the scalable and reliable communication and then focus on sensing and security aspects of things. So let's look into scalability. Take a simple example. We have a millimeter wave radio and we want to serve these 5 users. How do we serve it? With a directional beam. We serve one device in the first time slot, and then you need to switch the beam to another direction to serve second device in second time slot, then third, and so on. This approach, first, it incurs high latency because more the device you need to wait, each device has to wait for their turn to get served. At the same time, as I have explained, millimeter wave has extremely high bandwidth, more than 2 gigahertz. And if the demand for a particular user is not enough, if there is an IoT device which is sending a very small amount of data, but they are latency sensitive, they need to get the data as fast as possible. So we are not filling up the entire bandwidth of the frequency axis, the y-axis. So the colored portion represents the user demand, the amount of resources that are actually being served to the user. And you can see there is a lot of wasted resources. Yeah, this is using a phased array architecture which uses a single RF chain. Thank you. So now, because of these wasted resources, we get a lower spectrum utilization and it limits scalability, and it doesn't support any flexible resource distribution to these multiple devices. Now, why can't we serve multiple devices at the same time? We can do that. There is a technology, frequency division multiple access, very popular for sub-6 network. While in sub-6, you use an omnidirectional pattern, so every direction gets the signal, right? But in millimeter wave, if we want to serve with frequency division, what we will do, we will take the entire bandwidth, multiple subcarriers, divide it into 3 parts, F1, F2, F3, let's say, and then distribute F1 to user 1, F2 to user 2, F3 to user 3. But to do this in millimeter wave, to support 3 users, we need 3 concurrent beams, which have high SNR or high signal. Now, what is the challenge in creating 3 concurrent beams? If we use the existing technology using phased arrays to create 3 beams, then we will lose power per beam. The more you split a single beam into 2 beam, 4 beam, 8 beam, the power will go down by half, right? So less power means low throughput, low coverage, low SNR, we will lose a lot. We cannot scale it. We built Flexible with a goal that we can split my signal or beam into 3 directions to serve these 3 users without losing power per beam. Okay. Now, one way to do it is, of course, you can put more power, pump more power, get it from the grid, and then serve these users. But can we do it by keeping the same total power across all these 3 systems? So it looks very counterintuitive. And to understand this, we need to fundamentally understand what is a beam pattern. What is a beam pattern? A beam pattern is a distribution of energy in space or along the direction axis, right? Or at least this is what we taught in school. In reality, a beam pattern is a distribution, a two-dimensional distribution of energy in space, not just across the direction, but also across the frequency. Okay, it is an axis that we usually ignore, but we cannot ignore here. Now, as you see, the beam is narrow in direction, but it is spread across the entire frequency band. So even if we are serving a user one with a small box of frequency, the remaining resources or remaining power is just wasted in space. Even if you take the middle case, you have three beams. Each of the three beams are narrow in space, but they all are extended over the entire bandwidth, which leads to wasted power. So how we solve this problem is, what if we can take the energy in the wasted band and give it to useful band? And we can actually do it. We developed a new hardware architecture and prototype, which is capable of distributing energy only in the desired frequency band and not elsewhere. So the beams are still narrow in direction. If you see all three cases along the direction axis, the width of the beam is the same. It is just the power is redistributed from the other frequency band into the desired band. So the three beam pattern that you see, the height of the beam pattern or the SNR of the beam pattern remains same in the frequency band for the user. Outside the band, we don't care. Is this clear? So how can we create these flexible concurrent beams? We realized traditional millimeter wave architecture, which uses phased array, are not capable of doing this. They cannot create frequency dependent beams. So we started looking for some new hardware architectures. And we come up with a new architecture, we call it delay phased array. This architecture looks similar to a phased array. It has a single RF chain connected to an antenna array, multiple antennas. Each antenna is fed via a programmable delay element and a programmable phase element.
This guy, yeah, he knows our group and he used our hardware.
Professor
Extreme wave.
Sorry, Tum, I think you were. So thankfully, I think as someone commented out, we collaborate a lot with Professor Gabriel Rabes, and I will show some of the hardware that we have built through collaboration and getting from them. Thank you. Okay, so let's see how we can use this new hardware architecture. If the traditional phased array we use, there is no delay element, there is only a phase shift element. So we add an extra element into the phased array to achieve
I'll combine the data into one single RF chain and then.
Okay. So let's look into how it works, right? So to understand the basic functionality of this system, we need to understand the fundamental building blocks of the system. Okay, let's just consider a very simple case of two antennas. And we consider two cases, one with only phased array and second with only true time delay array, time shift array. Now, if we take the phased array and then we program the relative phase, the first antenna gets a 0 phase, second antenna has a relative phase of 5, then the beam pattern that we get is a narrow beam. As I have explained before, it is narrow in beam, but it is spread across the entire frequency. What delay can do, it can provide a relative phase of 2 pi f tau. So the beam, you can see for a given tau at second antenna, the phase is a function of frequency. In fact, it's a linear function of frequency, which will generate a response which is linear in frequency space curve with a slope. The value of slope will depend on tau. Okay. Now, what happens in a delay phased array? We have both phase and delay, 2 pi f tau plus pi. So we can take this line, we can change the slope by changing tau, and we can also change the intercept by changing phi. So these are the basic fundamental building blocks to create our desired beam pattern. Okay. Now, the patterns that we require are, so you can see that these building blocks are this linear element. It's linear in frequency direction plot. But the pattern that we require are extremely non-linear. As you can see, there is a null at the center. So how do we achieve this non-linear pattern using linear building blocks? To understand this, let's look into a case with 3 antennas. If we look into the contribution of first 2 antenna, it creates, you can see the response where the brighter color is the high energy, dark color means low energy. And the high energy is a line with a positive slope and orientation at the center. The second 2 antenna, last 2 antenna, creates a response with a negative slope, which is shifted so that the null appears at the center. Now, if we look at the response of all 3 antennas together, then we can achieve our desired response, which has null at the center and high energy in the band of interest. So we even with 3 antennas, we can achieve close to what we desire. Okay. With 3 antenna, it may look a little blurry. So we can add more antenna. With 8 antenna, we can create an image which looks similar to what we desire. It is the beam is extremely narrow in space, and in frequency, it can split the beam into 2 beams to serve 2 users. Now, the last one of the main challenge here is to create an arbitrary beam. How do we program the values of phase and delays in this architecture? So to understand how we'll estimate the phase and delay value for a real hardware, I formulated it as an optimization problem, and I solved it in a closed form expression. So this is the formula for delay tau n for antenna n and phase phi n at antenna n. As a function of some parameters, for example, the total bandwidth B. This is a simplistic formula where we assume that there are only 2 users, each having bandwidth of B by 2 half at 2 angles, theta and minus theta. For a more generalized formula, it is in the paper. If you're interested, we can discuss. So without going much into the proof of the formula, I want to share some insight that we got while deriving this formula and by looking at it. This is first time that we have kind of come up with this concept of multi-beam and first time derived this formula. So this thing, you may not find it in any textbook. So let's understand. We know that phi is modulo 2 pi because the value of phase cannot go beyond 2 pi. After 2 pi, it wraps around to 0, right? We made a similar observation for the delay as well. The delay here is bounded by modulo 3 by 2b, so bandwidth B. What it means is that to create these patterns, we don't need longer delay lines. We have bounded delays. And generally in hardware, creating longer delay lines is always hard. You have to deal with matching constraint for large bandwidth and so on. So this makes our system more practical and realizable with the current hardware with a limitation of total bounded delays. And these value of delay is independent of antennas. So you can even scale it to hundreds or even thousands of antenna with the same hardware. So we found these requirements for the hardware, and then we also built this hardware. This is a prototype that we have built at sub-6 band. These delay elements we could not find available online at millimeter band. In fact, it's extremely hard to build at millimeter wave. So our first prototype is at sub-6 band. This box you can see is the delay element. This is built by Professor Gabriel Raves at extreme wave. And then we build all the system around it. We have a phase shifter board, which has 8 phase shift ICs, which can do phase shift 0 to 360 degree. And then we have an FPGA board, which can provide control and power to all the components in the system. Finally, connected with a splitter, which combines all the 8 signals into a single signal, which goes into our ADC and DAC, which we implement using USRP. Now you can see the response, which we collect over the air. Y-axis is frequency, x-axis is angle. There are 2 users at roughly minus 30 and plus 30 degree. And we can see that both users are getting extremely high SNR in their desired band, which is marked in red box, while we are not wasting any power in the undesired band outside the red box. So we are able to achieve what we desire, right? And we kind of, for the first time, we have shown that such kind of architectures are not just theoretically possible, it is realizable with the true hardware. We have done a lot of simulation to verify large-scale scalability constraint, and I have compared them with a couple of baseline. One of the baseline is traditional single beam, which creates narrow beams in space, which cannot serve multiple devices at the same time. It has to serve in a TDMA fashion. Another baseline that we have already seen is a split array, which reduces power per beam. It can serve multiple devices, but it will reduce throughput and SNR for each device. There is one very interesting paper recently that came from UCLA, which also uses true time delay. but they only use true time delay. They don't use a phase shift. So what they can achieve a beam pattern which is a line, straight line in frequency direction curve. So this is also very helpful. You can use it, for example, to do a single shot user finding, or if you want to, let's say, estimate the direction of the user, what you can do is you send a single snapshot of this waveform, and the direction will map into frequency. You observe different frequency, which frequency you receive maximum power will give you direction of the user. Compared to a traditional approach where you need to scan multiple direction over time, which takes a lot of time resources. But this is not useful for our application. If you want to serve multiple devices, as you can see, each user, V1, V2, V3, receives a very tiny fraction of bandwidth per device, which is not enough to meet their demand. Maybe good for some IoT device, but not for AR, VR, or high throughput devices. Our system is extremely flexible. We can configure the bandwidth per user the way any way we want. It's a flexible number, and we can support high bandwidth for some devices, low bandwidth for other devices. And more importantly, we are not wasting power in any undesired direction or frequency band. Truly flexible system to support multiple users. Now, we implemented this with our simulator, with a traffic generator, which can generate multiple amount of traffic for around 100 users with different latency constraint and throughput constraint. And then we see that overall the latency we can reduce compared to baseline by 60 to 150%. And because we are utilizing these resources more optimally, we can achieve overall higher throughput up to 3.9 times compared to baseline. And all these gains are thanks to the flexible way of allocating time frequency resources to multiple users in millimeter wave band. Any question on this part?
So your design, did you ever really use the modular on the time?
Yes, we have to use modular on the time. To give you some numbers, the delay element that we got in the hardware has a maximum range of 1 nanosecond. It cannot go more than 1 nanosecond, which means that if you remember the calculation 3 by 2b, which is 1.5 divided by bandwidth, for 1 gigahertz bandwidth, the thing that we need is 1.5 nanosecond, right? So it falls within the limit for two beams. And so we don't need to go beyond. With the practical constraint of the hardware, we can achieve 2 beams. If we want to go more than 2 beams, then the requirement is higher. We need a longer delay lines, and that is not practically possible with current hardware. We need to build a new hardware which has longer delay.
So sorry, if we have misunderstood the answer. Did you say that the delay, the hardware was supporting large enough delay, you do not need to use the modular operation?
For 2 beams, we did modular. We used modular operation. That is a necessity, because if you don't use modular operation, the thing which is inside modular will shoot up, because it's a function of n. For larger n, it would become a large number. So we always have to use modular operation. Okay, so I will go in the second part or a second work, which so far we have improved the scalability and multi-device thing. Let's focus on a single device for a while, and let's see how we can make the link more reliable for this device. As I have shown before, these are narrow pencil beams, and if you move your hand around, you can easily block this link, right? And that will reduce your reliability. So we built Reliable. In Reliable, we split this beam into 2 beams to serve the same user. One link goes via the direct path, another link goes via some reflector and reaches the same user. Okay. Now, why 2 beams are better than 1? When a blocker blocks a single beam, it completely occludes it and brings outage. While in multi-beam, if the same blocker blocks the link, it doesn't block all the links at the same time. It's less probable. So if one link is blocked, the other link is still active. So overall, we can still maintain a reliable link, either one of the 2 beams. So very simply, we can avoid a single point of failure in a multi-beam system to establish a reliable link. We built Reliable with a couple of requirements. One, we have to achieve high reliability. That comes as a corollary of using multi-beams. Now, if you recall my previous presentation, if we split this beam, we are going to reduce power per beam, right? So does this mean, are we reducing the throughput and data rate in our system here? In fact, in our earlier prototype, we observed some reduction in data set. But we developed a new class of multi-beam. We call it constructive multi-beam, which can ensure that we can achieve same level of throughput compared to single beam, and in some scenarios even higher than that. Okay. Again, it looks counterintuitive. I will explain in the next couple of slides. I have implemented it on hardware. It is easy to create. We don't need any new hardware like delay lines for this. This can be done with traditional phased array architecture, and we have made it protocol compliant as well. So let's look into how can we provide high throughput. I will start with a very simple example, and I will add more complexity as we go ahead. Okay. So let's consider a simple directional link in the left and our multi-beam on the right. We have same total power for both systems, A square, which means that we are sending a signal A in the single beam. And this is a simple setup. So let's assume that the path loss or the environmental factors is not present there. So the receiver just receives A. Okay. Now the SNR in this case would be proportional to square of the signal strength, which is A square. Let's see what happens in multi-beam case. We have signal A by root 2 and A by root 2. Why A by root 2? So that we can ensure that the total power is the same. We are not using any extra power to create multi-beam. Now, when these two signals, when they add up at the receiver, A by root 2 plus A by root 2, which gives root 2A. One thing observe, the signals are adding at the receiver, not the power. Okay. When these signals add up at the receiver, if we compute the SNR, it becomes a square of the signal, which is root 2A square, becomes 2A square. So if you compare with the single beam case, we have already achieved twice the SNR, which can lead to higher throughput. Now, here we have kind of assumed that the two paths are equally strong, and the path loss or the environmental factor is 1 for each path, right? So even though it is a simplistic case, it demonstrates the capability of a system to achieve higher rate. Okay. Now let's add some more channel effect into the environment, into the setup. Let's assume that the reflected path suffers from an additional phase shift of e powered by j sigma. So sigma is related to direct path. Direct path still has attenuation of 1. Reflected path has e powered by j sigma. Okay. Sigma is the extra phase shift. What happens in this case if sigma is 180 degree or opposite phase? The two signals will add up in opposite phase and they will cancel out each other. This is destructive multi-beam. We do not want this. Okay, we lose all these signals. So what we want is that the two signal has to add up in phase, that we call constructive multi-beam. How do we achieve constructive multi-beam? We need to ensure that the signal add up in phase. And to do that, I modulated one of the reflected path beam with a negative phase, minus sigma. So when you do the math, when the two signal add up, you can see that sigma and minus sigma will cancel out, and we achieve the same signal strength root 2A and the same SNR 2A square. So with this modulation, our system is not affected by additional phase acquired by the channel. So one thing to take away message is that we need to do phase control to achieve constructive multi-beam. Is this enough? We are still missing one factor. That is, we kind of still assume that the two paths are equally strong. What happens when one of the path, typically the reflected path, is weaker? Okay, let's model this. Let's say the attenuation factor is delta. You can say delta is less than 1. In this case, I will not go into math, but if we also modulate one of the reflected beam by the same factor delta, we can ensure that SNR will be proportional to 1 plus delta square times A square. You can validate if delta is 1, like our previous case, then 1 plus 1, 2A square. And what happens when delta is 0? Let's say there is no reflector in the environment. We are in anechoic chamber. Then we get the SNR just A square, which comes from the direct path. So this suggests that adding an additional path, just the environment itself, just the presence of environment gives us higher gain. This is not limited to two paths. If we have more paths, more reflectors, which are strong enough with larger delta, it will just add up 1 plus delta 1 square plus delta 2 square and so on. But extracting more parameters, estimating more parameters is usually more noisy. So we limit ourselves to maximum 1 or 2 reflectors. So the second component that we need for constructive multi-beam, not just phase control, we also need power control. how can we do phase and power control with traditional phased array architecture that we need to look into. So let's, before that, I want to convey some of the measurement results we did with our hardware, and we kind of showed that the reflectors are actually strong, because if this reflector is not strong, then we cannot support this multi-beam. And most good reflectors like metal or glass are extremely strong. Other reflectors like a concrete wall is good enough with 5 to 10 dB of attenuation, which will still improve, if not improve throughput by too much, it will at least provide us good reliability. Now, let's look into how do we create these constructive multi-beam with phased arrays. We take the phased array, which has a single RF chain connected to an attenuator and a phase shifter. If we want to create a beam at an angle, say phi1, we know that a beamforming weight vector that we need to apply across these antenna array, W phi1. Okay? I won't go into detail what W phi1 is, but let's say if we want to create another beam at phi2, it is a vector W phi2. And with the principle of superposition, if we want to create both beams phi1 and phi2, we can simply add W phi1 and W phi2, and this will create two beams at phi1 and phi2. This is not enough. Why? We haven't yet ensured that we can achieve constructive multi-beam, for which we need to make sure that we can estimate parameters delta and sigma and apply it to precode the beam. And we do that by multiplying the reflected path beam with a factor delta e powered by minus j sigma to ensure constructive combining of two beams or two sigma. Now, to ensure that we don't take more power from the grid, to preserve total radiated power, we need to also normalize this beam pattern so that assume that the W phi1 already has a norm 1, then this multi-beam pattern would also be seen norm 1, which will ensure that we are not taking more power to create these multi-beams. Now, we take this W multi phase and attenuation values from this formula, put it into our phased array, and we create practical. Now, we also make it protocol compliant. I won't go much deeper into this, but if you know the protocol, it has a beam training phase and data phase. The beam training phase scan multiple beams to figure out, traditionally it tries to figure out the direct path angle to the user, but we leverage it to get both angles phi1 and phi2. And then we design additional protocol which uses reference signals, in this case, two reference signals to estimate the additional two parameters, delta and sigma. If you have more parameters, we can use more reference signals, which are already present in the protocol. So without going more into the math, I want to show some cool hardware prototypes that we have built to demonstrate this. Again, thanks to Extreme for providing the phased array and all the other setup we have built in our lab to ensure that we have a test bed which can do very precise phase and gain control required by our reliable multi-beam. And we have built an FPGA platform which can scan beam as fast as 2 microseconds per beam. Okay. Generally, for millimeter wave, one minimum symbol time for data communication, 1 TTI, is 1/8 of a millisecond. And this is kind of 100 times faster than that. So our system is capable of doing real-time beam scan to understand these effects with real hardware, with real mobility and real time. I'll show some demo on this. But going further, we have a large 1000-size codebook, which means that we can already store these beam patterns into the FPGA memory and then load them from there. It is already ready with 5G beam radio waveform. We have tested with different SDR. In this case, I'm showing a Pluto SDR, which is extremely cheap, low power SDR. We have tried with USRP, Xilinx FPGA platform, and other SDR depending on the requirement, on your throughput, power, and so on. This is a setup which is compact, and we can just take it around, and we have done a lot of experiment where we put it in a car and drive with it, or we just take it in our hand and we run with it.
So are you saying that the system is constantly just opportunistically trying to find a reflector and use it? And how often is it doing that kind of adapting to the environment?
So the way we have conducted the experiment is we have scanned all the beams in all different directions. And then if one beam is pointed towards the reflector, it will give some high signal strength corresponding because it will detect the presence of the reflector. And we can save this data. And then in post-processing, we can realize basically where the reflectors are and where the users are. So this system, basically, we have developed as a data collection platform to get data for every beam. Every 2 microseconds, we will scan. If you want to scan, let's say 100 beam, within 200 microseconds, we have a data corresponding to different directions. And then from there, we can extract reflector and user angle. Does this answer your question? I have used this setup to build a reliable multi-beam forming, which I just talked about, and a couple of other applications for mobility tracking, for video streaming as a collaboration with Professor Pam, and also some more latest work in vehicular networking. This is one of the demo we have shown. This is a setup in Miramar Air Show, where we put our setup on a bot. I will move the bot around. What I'm plotting here is the top plot is a time domain diagram, which shows all the data corresponding to one beam scan. So going from left to right, it scans beam from -60° to +60°. Okay, and where you see very high signal strength, that's the point corresponding to the angle of the user. In this case, if the angle of the user is 30°, you will get signal high at 30°. Basically, 30° beam will give you highest signal. Now, if you move this device, when it is moving left, you can see that the entire beam moves towards the left, from which you can estimate user angle. If there is a reflector, then you will see one of the reflected path also becomes high. Bottom just demonstrate a high bandwidth capability along the frequency axis. So you can see it basically works in real time with real setup. Okay.
At least on the diagram, does it mean there are multiple reflectors there?
Those are the side loops most likely, because we did the experiment in a very open area. So I doubt they are reflectors. Okay, so we have done a couple of experiments. In fact, some of these experiments in the, let's say, Warren courtyard had strong reflectors with the glass wall that comes in the Atkinson Hall, and that provides us additional path to utilize the reflected path. We have some results. One of the important results I will show, where we create these multi-beam and we ask some volunteer to walk and cross this link. Now we plot the SNR as a function of time. The red curve is the baseline. As you can see, when the person blocks the beam, then the signal goes down. It goes below a certain threshold from which you cannot recover the link. It goes into outage. While our multi-beam, which is in blue, always remains above this threshold. There might be some glitch when the reflected path is blocked, but when the direct path is blocked, it doesn't go as low as single beam, which means that if there are occasional blockages, it can adapt to that system and make sure that the beams are always stable and reliable. The throughput of the two system is pretty much similar. The y-axis is 0 to 30 dB. So even if there is 3 dB higher throughput or SNR, it is not very visible. But if you see closely, the blue curve remains pretty much always above the red curve. So it demonstrates that we can maintain high reliability and high throughput with directional millimeter wave links. This work has been published in SIGCOMM and Infocom and has been also widely popularized by popular news articles. I have also won a Best Poster Award in one of the projects at Harvard. So any question in this part? I can summarize this work and then I can. Right? So basically what we have seen until now is in Flexible, we can serve these multiple devices at the same time using different frequency bands to serve these multiple users. And this ensure that we have scalable and low latency links. In Reliable, again, at the same time, we serve the user with the same frequency band, one user at a time. And this ensure that we can create reliable link with high throughput. Of course, we can combine the system with the idea of new architecture, new algorithms, new prototypes to show that we can achieve the best of the both world and provide millimeter wave link that is scalable, low latency, reliable, and high throughput. So with the interest of time, I will quickly go to the second part of the talk, and this would be very brief. We'll be mostly touching at the high level without going much into the details. So let's look into one of the challenges of mobility. Okay, when we have multiple users in the environment, right? In this case, we have 3 users. And if these users move around in some random mobile pattern, it's extremely hard to keep track of these different user mobility patterns and make sure that beams are aligned. with 1 or 2 devices, maybe you can solve this problem, but when you scale it to tens of devices, then it becomes a big challenge. At the same time, blockage also become extremely hard because now these multiple links get blocked at different times, and you need to make sure that you can track each of the links. Okay, so it's a very challenging problem. To solve this problem, we are looking into a system where we can augment our communication radio with an external radar. Now, a radar works in similar frequency band, like in millimeter band, but it has extremely high bandwidth. It's extremely low cost. You can purchase a TI radar with a few $100, and it works in ISM band, which means you don't have to get a license to operate this radar. So it's very easy to deploy with the infrastructure. And the advantage is, because of high bandwidth, it can provide extremely high resolution in estimating the location and tracking these devices. So it makes sense. It can also predictively predict the blockage movement before the blockage block the link, which would also be helpful. So with all these good benefit, what are the challenges that will limit this deployment? One of the challenges that we are looking into is the radar's cold start problem. What it means, a radar sees bunch of points in the space. Okay, it doesn't know what is the context of this point. Which of these points are active user that it need to track, or which of these points are some reflectors which can provide help the link, like in MM reliable, or which of these points are a blocker which are going to block the link in next couple of seconds. So how do we ensure that radar gets this context? Okay, so how do we tackle this problem? We have the radar system, and as you can see, it gives you the data in the form of distance and angle map. So basically, every point in this plot is some objects in the environment at a certain angle and certain distance, but the radar doesn't know what these points are. Now, to obtain context, some people have shown that we can maybe deploy a GPS device for every objects and so on, but we don't want to add any extra complexity. Let's use something which is readily available in this setup, which is our radio. Now, radio we can use as a bistatic sensor. What it means, it collects regularly data from different beam scan from multiple users, and you can get something like a RSS, which is receive signal strength, as a function of angle for each user, from which you can estimate roughly what is the angle of direct path, reflected path, the location of user and reflector. So we take this data, we map it into a distance angle plot, which is similar to how radar sees, and then we feed it to the radar so that the radar obtain the context directly from the radio right there. And with this context, the radar can now operate smoothly, and it can help in tracking user devices and predicting blockage. I won't go into deeper into all these algorithms, but one thing I want to emphasize is that our objective is to make sure that this feedback doesn't come very often. Otherwise, it will violate our one of the requirement that now we need to use the radio to do most of the heavy lifting job. So this feedback come very less frequent, every 1 or 2 seconds, or even lesser. While in that duration of, let's say, 2 seconds, the radar works standalone. It can help track the devices, predict blockages, and identify reflectors. So let's look into some of how we actually implement this setup. We have a platform with our radio and radar, which are synchronized. We did a couple of indoor and outdoor experiments. We make sure that there are some reflectors so that we can also demonstrate a link with via reflectors. If I emphasize on one of the evaluation scenario, let's consider 2 users in front of the radar and radio platform, blue and red users, and they are just crossing each other. Okay, so as you can see in the angle versus time plot, the red user start at plus 20 degrees, the other user start at minus 40 degrees, and then they both merge together at some point around 5-second mark. But then this is the case with without collaborative learning. It kind of thinks that both users now started walking together in one direction. That's not actually true. The other user has moved in the other direction. We cannot resolve such ambiguity using radar alone. With the help of our contextual learning from the radio, we can avoid such cases and resolve location ambiguity and correctly estimate the trajectory of both users accurately. So this setup of collaboration between radio and radar is extremely helpful in such cases. And you can imagine in more than 2 user scenario how helpful this could be. Now, let's look into another topic. This is a joint work with my colleague Rohit Reddy, and I will present high-level idea for this in just 2 slides. So let's imagine one of the most important deployment of radar today is in automotive vehicles. Let's say there is a white car with one of these radar. The advantage, it works in all weather and it provides a very good estimate of distance and velocity of different objects so that you can maintain safe distance while driving. But now this red car suddenly is a mischievous person. It turns on a device, some spoofing device, and what happens is suddenly a new phantom car, a random car appears in front of the white car. Naturally, the ADAS system, the autonomous system in the white car will trigger a response that will apply brake immediately, and using this phantom brake, it may even go into accident. So this is extremely dangerous attack, but such kind of attacks are actually feasible. You can spoof the radar because if they have the capability to spoof distance and velocity that the radar estimates. Okay. This is not a new concept. In fact, some of the prior work have tried to validate these attacks. What they do is they use a spoofing device, which is an active transmitter. It generates the waveform, which is similar to radar, the FMCW waveform, and it radiates back to the radar with the hope that this new waveform will create an additional object in front of the white car. But they require active transmission, which is in most cases in one of the prototypes achieved by even using a wired synchronization, which is not feasible in a real world setting. How can we cut this wire? We put a different device. Our device is not based on active transmission. It is based on reflection. What it does is it receives the same radar signal from the white car. It modulates the signal and reflects back towards the radar. Okay. We have shown that some of these modulation can generate velocity and distance spoofing independently, and this doesn't require any active transmission, and it eliminates the requirement for synchronization. So without going into detail, if I want to show one of the results, this is the setup we have. You can see there are 2 phased array. Again, thanks to Extreme Wave for providing this array so that we can build this setup. We have a USRP to do this real-time modulation of the signal that we capture from the radar, which is mounted on the car. We use a LiDAR just for the ground truth. We are plotting distance and velocity. As you can see, the red curve is basically if the car is static at a certain distance of 30 meters with velocity 0, we will get that over time. But when we turn on our spoofing device, then what we estimate is that the distance has started going down. Velocity, let's say, start from some number minus 10 and it goes to 0. It kind of mimics as if the front car was moving at a high speed and it suddenly applies brake. Right? Distance will go down, velocity will go down, but that's not actually happening. It's just a hallucination that we can provide to the radar to show how dangerous this attack can be. It can mimic a real world braking pattern of the car. We developed a couple of countermeasures to make sure that this attack are not possible using multi-radar fusion and a couple of other ideas. I won't go into detail of there, and I will conclude here. To show some of the ideas that I want to build on this, and as a faculty at RPI, I want to work on building across all these 3 areas in communication, sensing, and security. I want to ensure that the communication links are reliable and low-power network. They can be achieved with low power. In sensing, I want to ensure that we can use more recent techniques from AI and develop more multimodal sensors to deploy these sensing algorithms. And I want to build more such testbed to demonstrate spoofing, jamming kind of attacks. To go a little bit deeper, I have shown this spectrum. So far, we have been using sub-6 band and millimeter wave band. There are new bands that are coming up. FCC is planning to release mid-band, which is between 6 to 24 gigahertz for communication. That has been traditionally used by satellite. So now communication, 5G, will coexist with satellite, the same band. We need to ensure and design new prototype and algorithms so that we can manage the spectrum and interference for the coexistence. I have shown unreliable, which utilize reflectors, right? If the reflectors are weak, we may not get a lot of gain. What we can do, we can augment the infrastructure with some low power intelligent surfaces, which can enhance these multi-beam links. And it provides a new advantage of utilizing these reflectors to create 2 simultaneous beams. Similarly, for sensing, we have kind of already demonstrated these 3 sensors together. We can add more sensor into the modality like ultra wideband or terahertz sensors to build more robust sensing platform. And we can even combine the sensing with communication. For example, the radar has same kind of antennas that we use in radio. What if they both share the antenna and some kind of algorithms to create a single holistic system for sensing and communication? It will improve spectral efficiency and utilize for the use cases that I have already demonstrated. Similarly, in security, I have shown a spoofing attack, but we can try more attacks, for example, which can spoof user tracking or even activity recognition that is possible with some of these sensors. And also, we want to make sure that we can do it in a way that is privacy preserving. It means that if the user doesn't want to share its location with infrastructure, it should have the capability to do so. How can we develop those capabilities? We can also build a new test beds. In fact, this is an active work with my collaboration with some of my lab mates and also some of the work that I did at VMware and some of the ongoing projects where we are deploying a private 5G network in our lab. They can in fact connect with one of the my phone right there. This base station is fully programmable. It is based on one of the open source code using SRSRAN and open air interface. And we have developed a new code base in this open source platform. We call it a controller, which can add new functionality. For example, in Beam Armor, it does interference nulling functionality using a MIMO setup. So building on this new testbed and systems on a large scale will be one of the goals for this research. Obviously, building such large scale system doesn't come so easy. I'm very, very thankful to all my mentors and collaborators, and especially the undergraduate and master's student who I have worked extensively. And these are the main powerhouse. Like these are the people basically that have designed the FPGA code, the USB, the PCB that we have used and deployed, and all the extensive indoor-outdoor experiments. I'm very, very thankful to the team. Obviously, I cannot put everyone into this space. I will talk a little more about other people, but these are the people I have directly worked with and collaborated with to build these large-scale systems. I'm very, very thankful to the entire WCSNG lab, the wireless communication, sensing, and networking lab. Basically, when we started, it was just a few PhD students. It has grown to such a large group, as you can see in the pictures. So yeah, basically, I'm very, very thankful to Dinesh. He introduced at the beginning. It is true that we have been mostly working as a colleagues, then seeing him as an advisor, and that has helped a couple of night outs that we have done together. A couple of I came from a theory background, so it was extremely hard for me to. Dinesh came at the right time. Thank you.
Eating my lunch. I haven't had lunch. So I was sitting in my office and
yeah. So yeah, thanks for all the hard work. Like one main thing I want to emphasize is Dinesh believes in you to the core. Like even if you feel like the research will not work, he won't give up. And that's the attitude which I have learned, and I kind of adopted that. Okay, it is extremely hard to convince Dinesh, so we need to do more experiment, more analysis, more algorithm development, so that we can finally convince him that either it works or it doesn't work, and we have to drop it and move into something else. But thanks to that, some of the very counterintuitive ideas that I have presented that come from these group meetings and random discussions and standard walk and talk. We basically talk almost every day to discuss these new exciting ideas. Thank you very much for all the support. This last picture is basically taken during one of the, just immediately after one of the Mobicom conference deadline, and it was Dinesh's birthday. His birthday pretty much always fall on the deadline day. So he's always there until night. Deadline time. I'm also thankful to all my friends around San Diego. I have gone for multiple hikes, pretty much explored all the areas around, and these are a couple of people I randomly usually hang out with, a couple of lab mates and other friends here in San Diego. I'm thankful to my flatmates and also my lab mates, Agrim, Ashwin, and Manideep, who has been extremely helpful. I see them in lab, I see them at home, so they can't escape them. Thankfully, when I do the cooking, they do the dishes, so it has been a good collaboration. Finally, my family has been always the part. Picture you can see it was taken during the wedding of my brother, and my mother and my they have been extremely supportive for my ambition, and thanks to them, I was able to finish the PhD, or I was able to do the PhD. Also thankful to my family here in USA, my uncle and my cousin, who is also among our audience. Daksh, can you stand up? uh, they live in Pittsburgh, and they have always been very helpful. I visited them a couple of times, and their company and support always helps me and motivates me. So I will end up with basically giving a bigger picture and vision for all the work I have been doing for the next generation beyond 5G. Okay, so our founding fathers in communication, they used to work with circuits and devices. Say Marconi or Maxwell, you can see they are using some devices to work on to provide new communication technologies. Then came Shannon theory. Shannon simplified these complex devices with very, very simple linear models, linear channel, linear circuits, so that we can build the foundation of modern communication system with OFDM and MIMO techniques. Now, when we look into designing the future generation of network, we need to combine the learnings from the two system. We need to understand circuits very well. We need to understand theory very well. And we need to understand how they interplay to build this next generation of network to even push for higher data rates, lower latency, high scalability, and so on. And finally, when we deploy this network, we collect a lot of data. So obviously, we need to take advantage of all the advances in data-driven techniques to further improve communication, sensing, and security aspects of this network. I have built this system as a system-oriented person. This kind of approach always inspires me to build new algorithms, new hardware prototypes, and new applications. Thank you very much.
Could you online as a question? Hopefully we can hear the online.
Yeah. You can directly speak online.
Hello.
Yeah. Hey, Vishnu.
Hi, Ish. Yeah, fantastic talk. Thanks for a very wonderful talk. So I am an AI researcher. So as an AI person, I was. This is more of an exploratory question. You know, as an AI person, you mentioned that you can use AI for wireless sensing. Can you give me what are like some approaches you could use? What are some methods, AI methods that you could use for wireless sensing? Of course, you have data. You could have like a learning algorithm that uses like some ground truth labels to design a model. One thing that is unique about AI is that we leverage these patterns. In images you have these vision models that are invariant to rotations performed on images, or they are equivariant to, let's say, translation. So what are some of these symmetries, or these invariances that are particular that are unique to maybe millimeter waves or radios or like wireless data in general?
Yeah, thank you very much. Just to introduce, Vishnu is one of my undergraduate classmates, and right now he is also a faculty at University of Buffalo. Thank you very much for the question. Machine learning has basically a system which, whether you like it or not like it, you cannot avoid it today. Okay, so we need to look for ways where we can utilize these tools. They are extremely helpful in some of the applications that we have seen in large language models and images. How can we adopt it to wireless scenario? So one thing that I always feel is that we cannot blindly use or trust these tools to solve any problem in wireless. First, we need to choose the correct problem, which are extremely hard, which cannot be modeled with traditional signal processing, and which can benefit because the ML can model some nonlinear behavior of the system. So I can give one example, which in fact I have deployed in very recently. Let's say we want to track these different devices using radar. Right? It has multiple points in the object. They are moving around, and then we want to track these devices. Now we have seen a lot of work on tracking using camera images, using videos, right? can we leverage those networks, those ML algorithms for this particular radar data? Now, one thing that we need to ensure that to apply those models, we need to pre-process the data, which comes in a different form. Here you have wireless signals, IQ data, which you need to, we make it into an image. I have shown a distance angle image, right? That's an image which looks very similar to how a camera image is. And now, after doing such pre-processing of the data, we can ensure that we can retrain those existing models to work on our new data set. And we have, in fact, used some of the optical flow methods, which are popular in machine learning tracking on camera images, and that works pretty well on radar images as well.
I see. Yeah, very helpful, very helpful. The second question, like second part of my question was, what are some of these symmetries? Are there any symmetries like rotation invariance, translation invariance, or let's say with large language models we can say these transformers are permutation equivariant. So is there equivariance invariance principles that we can exploit out of this wireless data?
Okay, so definitely the variants that exist in camera images do exist similar variants in radar images if you pre-process them in a way that looks like a camera image. So there we can exploit these variants directly. In certain other examples, we may not exploit these variants. For example, one of the recent work that was popular and a best paper award in one of the conference where they model the entire environment. They can recreate the environment just by observing radio frequency waves at few locations, right? The neural field concept is very popular. They use it using camera. Just using few camera, can you reconstruct a 3D scene? They tried using wireless data to reconstruct the scene. So some of the techniques, for example, in this case, what we are doing with wireless has been taken directly from a well-known technique that exists in the field of camera and video processing. So if we can make sure that the data that we obtain in wireless is in the correct form, we can pre-process the data, then it can, my assumption is that it will retain the properties of invariance that exist in optical data, for example. I haven't done a lot of research on this yet, so I won't be able to comment very precisely, but this is something I hope to work on and we can collaborate for sure.
Wonderful, wonderful. Thank you so much. It's fantastic talk.
Anybody else has online or in person any more questions? I think we can limit to the committee. Thank you, everyone.
And please have these facts.
Yes. Over 8.
Online.
Can you stop it?